Hi everyone, thanks for tuning in today. My name is Abhishek and I'm a PhD student in the Autonomous Systems Lab at Stanford University. Today I'll be presenting work on COCO, for combinatorial offline, convex online, which is an approach for learning strategies for mixed integer convex optimization problems. The problem we're interested in exploring in this work is that of discrete and combinatorial optimization problems. These are optimization problems where some subset of the variables are discrete or binary. These sorts of problems arise in a variety of applications. In robotics, such problems can be used to model robots such as the Boston Dynamics Spot shown here, making and breaking contact with its surrounding. They can be used to model network or logistics management problems in operations research. Despite the advances made in numerical solvers for discrete optimization problems, they still remain challenging to solve in applications requiring real-time operating speeds, where by real time, we mean problems operating at rates of 10 to 100 Hz. In our work, we focus our attention on mixed integer convex programs, or MICPs. MICPs are optimization problems where the objective function and constraints are convex functions, but are made non-convex because of the discrete variables delta. Here, theta are the problem parameters that vary between each problem. For example, these parameters might include a new initial position of the robot, or a different resource allocation vector in a portfolio optimization problem. This leads us to the paradigm of parametric optimization. In this framework, we consider solving an optimization problem P of theta repeatedly for different problem parameters theta to yield new solutions x star and delta star. In many real-world applications, there exists underlying structure to this problem between theta and the solution. This leads us to the question of whether we can utilize data to leverage the structure to this problem and close the loop, so to speak, to more quickly solve this problem online. Before doing so, we first define the notion of a logical strategy. A logical strategy corresponds to a set of parameters and consists of the values of the discrete solution of the problem and which constraints in the optimal solution were active. The utility of this definition becomes apparent when we return to our original optimization problem. Imposing the optimal logical strategy on the MICP yields a convex optimization problem, which can be solved much more efficiently. This motivates us to try and learn a mapping between the parameters theta of our problem and the optimal logical strategy S of theta. We propose COCO, which stands for combinatorial offline, convex online. COCO consists of a two-stage approach. Offline, we solve a set of parametrized MICPs and tabulate the logical strategies found. We use these to train a neural network classifier that maps parameters theta to the optimal logical strategy S of theta. Online, we receive a new set of parameters. With a single forward pass of the classifier, we rank candidate logical strategies and use them to solve a finite set of optimization problems until either a feasible solution is found or the algorithm terminates with failure. We demonstrate the efficacy of our proposed approach through numerical experiments on a benchmark of robotics problems. First, we investigate the spacecraft motion planning problem, a fundamental problem in robotics that we model as a mixed integer QCQP. Our problem consists of 160 binary variables. We benchmark COCO against the commercial solver Gurobi and other state-of-the-art data-driven approaches for solving MICPs. We show that COCO outperforms Gurobi and the benchmarks in terms of solution time, as well as the average number of QCQPs solved before a solution is found. We further find that COCO not only finds feasible solutions to the MICP, but finds the globally optimal solution the majority of the time. Our next benchmark is that of the dexterous robot grasping problem. We model this problem as a mixed integer SOCP with 30 binary variables. Once again, our results show that COCO outperforms both the commercial solver and benchmarks. In fact, for this problem, COCO finds the globally optimal solution for the majority of problems and provides 100 times speedup compared to the commercial solver MOSEC. We refer to our recent publication for further details on our proposed approach, COCO. Thank you for listening.